Hello everyone, this is Krishna from Sony. In this video, I will explain about the paper titled StyleNerf, a style-based 3D aware generator for high resolution image synthesis. So this work is the result of a joint collaboration between Facebook AI Research, MPI Informatics, and University of Hong Kong. This paper explanation assumes a basic understanding of NERF on the part of the viewers, and this paper was published in ICLR 2022. So let us talk about StyleNerf. StyleNerf is a 3D aware generative model that is NERF based, and it takes as input a set of unstructured 2D images and synthesizes high resolution images with high multi-view consistency. So some of the features of StyleNerf are as follows. It essentially combines StyleGAN 2 and NERF++ to get the best of both works. It wants the high quality image generation as can be done with StyleGAN 2, and it wants multi-view consistency as you can achieve with a NERF based work. So to mitigate the inconsistencies caused by 2D upsampling, so they discuss in this paper that 2D upsampling results in certain inconsistencies. They propose multiple designs and they propose a better upsampling method, and they introduce a new regularization loss to achieve better results. So StyleNerf enables control of camera poses and different levels of styles, which can, and those the style transfer and the different level of styles can generalize to unseen views as well. And it also supports challenging tasks including zoom in and out, style mixing, inversion, and semantic editing. They show their results on all these ends as well. So there have a related work. There have been a lot of NERF based works recently, and these works are capable of multi-view consistent image generation, but they require posed multi-view images. They require camera pose for every view that they are provided as input, and the rendering process of neural implicit fields based method is slow. And there have also been a lot of image synthesis with GAN based works, and these GAN based works such as StyleGAN family, they are capable of high quality image generation, but they do not allow explicit camera control. Then StyleNerf belongs to an intersection of these two fields, a field which we call as 3D aware GANs, and it is a promising field, and some of the recent papers are promising, but they either struggle with high resolution images or produce view inconsistent artifacts. So how does StyleNerf works? Essentially, the authors start with this idea of let's combine NERF and StyleGAN to get the best out of both worlds, as I mentioned in the related works. The authors use NERF++ and not standard NERF. So NERF++ is a NERF variant that was proposed to handle unbounded backgrounds. I'm not going to go into the detail of how exactly NERF++ works, but for the purposes of understanding this video, all you need to know is that it is a model that has a separate scheme for handling the foreground and the background. So if you're dealing with human faces, the human face itself will be considered the foreground, and everything in the background will be considered background. So the authors had this idea, let's combine NERF and StyleGAN 2. So how exactly can we go about combining them is the next question. So let's have a look at their respective architectures again in order to understand how we can combine them. So on the left you can see is a StyleGAN 2 architecture, on the right you can see is a NERF architecture. So how does the StyleGAN 2 works? We start with a latent code Z, which we sample from a Gaussian distribution. We pass the latent vector Z through a mapping network, which gives us another latent space, by which is the latent code obtained after passing through the mapping network is denoted with W. And yeah, then this W is used to control the distribution of the outputs of the synthesis network. Actually, this W is then fed through another network, which then predicts the scaling of the different channels that are produced in the intermediate outputs of the synthesis network. And then yeah, we have this synthesis network which starts with a constant input of 4 cross 4 cross 512. It then generates a 4 cross 4 image followed by progressive upsampling to produce an 8 cross 8 image, then a 16 cross 16, and all the way till 1024 cross 1024 image. So this is a very broad view of how exactly StyleGAN 2 works. So, and this is the architecture of NERF. How exactly does NERF works is, in NERF we are trying to encapsulate an entire scene in a 3D grid. We sample points on that 3D grid, the XYZ, and the camera view of and we also need to, and as the final goal is to render the image, we also have a certain camera viewing direction which is denoted by theta and phi. So for camera viewing directions we deal with spherical coordinates. So we feed these this is the camera coordinates, the camera viewing direction, and the 3D point coordinates to a neural network which predicts the RGB color at the corresponding 3D point and the density value at the 3D point. And we do this for all 3D points along a ray, and then we perform volumetric integration along the ray to get the final pixel color. So this is how NERF works. So we have revised the StyleGAN 2 architecture and the NERF architecture. So what is the easiest way to combine these two architectures? So perhaps the easiest way can be that we start with the NERF architecture. We assume a 3D grid. We sample points on that grid. We pass them through a NERF MLP to get the color and density at each 3D point. Then we pass the color and density that we now have at each 3D point through not the density, but we pass the color value at each 3D points through a block of convolutional blocks that we have in the StyleGAN 2 synthesis network. So those blocks will refine the color value that was obtained by NERF. And so essentially the synthesis block, it refines the color values that was output by NERF, and we finally get the final output after passing through the StyleGAN 2 synthesis blocks. Then we perform the volume rendering to obtain the generated image. And yeah, so some of the specifics of StyleGAN 2, some of the features of StyleGAN 2, such as injecting latent vector W at different points in the NERF MLP and synthesis blocks, can stay the same. So we can still do something like that. So this is an easy way in which we can combine NERF and StyleGAN 2. It sounds reasonable, and so let us see how this architecture looks visually to have a better understanding. So as I said, we'll have your camera view direction P and camera pose, and we sample points on this n cross n grid. N cross n is this 2D image corresponding to which we construct a n cross n 3D grid, and we sample points on that grid. And yeah, we then apply positional encoding, which is a feature of NERF. You don't pass the coordinates directly into the MLP. You augment the points with their respective positional encoding. As I said, what happens in NERF++ is that you have a separate scheme for modeling the foreground and the background. So yeah, we pass the points through these MLPs, which gives us the RGB and sigma for all the points that we are sampling. Then we pass this RGB points through StyleGAN2 blocks and the synthesis blocks, and we'll have a mapping network and this latent vector Z, and the Z is passed through the mapping network to get the latent vector W. And yeah, with this is injected at different points in the architecture, because that's what happened in StyleGAN2, and we want to retain the good features of StyleGAN2. We want those features such as that which allows style mixing, and also that's why we have to do this this injection of W vector at different points. So we pass the RGB values that we have obtained at different 3D points through StyleGAN2 synthesis blocks, and that gives us the final RGB value at different 3D points. Then we perform volume integration using the RGB value at each 3D point and the density that we had obtained earlier, and that gives us the final image. But there are major issues with this formulation. The first of which is that this formulation is very slow and inefficient. As we know that NERF rendering is very slow. In fact, 2D GANs are 100 to 1000 times more efficient to generate a 1024 cross 1024 image as compared to NERF based models. Therefore, we never render the entire image in NERF training. We sample a subset of pixels and we only project rays from the camera that pass through those subset of pixels only. We don't project the rays that start from camera through and all the pixels in the image. And we also know that NERF consumes much more memory to cache the intermediate results for gradient back propagation during training, and thus this makes it very difficult to train on high resolution images. So while our previous formulation seemed reasonable, there are these two major issues with this. That's why we don't try to even train that. In fact, because NERF rendering, it takes about 30 seconds to generate one high resolution image with NERF, and if we have to spend 30 seconds to generate, and 30 seconds is on a very high-end GPU as well, so if we will have to spend 30 seconds to generate one training image for every iteration of training, the training would probably still be going on to the day of recording this video, and this paper would not have been published if they had gone through with something like that. So as I said, 2D GANs are much more faster than NERF. So let us understand why are 2D GANs faster than NERF. So the first thing is that each pixel only takes single forward pass through the network in case of 2D GANs. So this is true, and in case of NERF, we know that we project the ray that passes through each pixel. We sample n number of points on the ray, and we have to perform the neural network pass through each sample points. So every pixel in case of NERF takes not a single forward pass but n forward passes through the network. And also in case of 2D GANs, the way StyleGAN architectures have been developed is that the image features are generated progressively from coarse to fine, and the feature maps with high resolution typically have a small number of channels to save memory. So what is the solution then? How do we combine NERF and StyleGAN? So the authors, they do two modifications to speed up the forward pass. The first is that instead of performing volume rendering to get the final image, volume rendering is performed in the feature space and on a lower resolution as well. And instead of rendering a high resolution feature map, they generate a downsampled feature map at a low resolution and then employ upsampling in the 2D space to progressively increase towards the required high resolution. The second change is that instead of performing the complete volume rendering the way it's been formulated, they approximate the volume rendering with a modification which I'll go through. So this is what their approximated volume rendering looks like. Here IWNerf denotes the exact volume rendering output, whereas the IWApprox denotes the approximate version of the volume rendering. So as you can see in this formulation, IWNerf, in case of IWNerf, we calculate the color and density at all samples along the ray, and then the final ray color is computed by volumetric integration. So in IWApprox, we calculate density at all samples along the ray, and then the pixel depth is calculated by integrating the density at all the examples. So essentially this is similar to how in ray tracing we find the nearest point of contact as we project a ray that goes from camera onto the scene. So this is essentially similar to that. So we calculate density at all samples along the ray, and then we calculate the depth the depth of the object corresponding to that pixel by integrating the density at all samples. And then the final color is obtained by passing the ray sample at the pixel depth value through the color neural network. So why is calculating IWApprox faster? This is because we avoid doing the forward pass through this phi and c neural network. We are only doing forward pass through the first neural network and not the second one. So yeah, how we are doing this approximate volume rendering is that we are finding the intersection point of a projected ray, and we calculate color only at that point. So as we project a ray onto the 3D scene, the intersection point is the point at which the ray hits the 3D surface, and what we are doing is that we are only calculating the color at the intersection point, and we take that to be the final color. Now there might be some concerns that this approximation might perform poorly for translucent or transparent surfaces, but for the context of this work, they do not test on those type of objects. So this approximation works fine for the authors. So how would the revised architecture look like? So essentially it would look like this. As we can see this, they have earlier this 2D aggregation was done at the very end. Now the 2D aggregation is done in the feature space, not in the RGB space, and it's done for a lower resolution. So we start with this n cross n frame. At this n cross n image plane, we project rays passing through the image pixel that enters the 3D scene. We pass these points through a neural network that gives us a feature value associated with each 3D points. Then we aggregate those 3D feature maps to get a 2D feature map, and that 2D feature map that we get corresponding to our image plane is then passed through StyleGAN2 blocks. And in these blocks, earlier we were not doing any upsampling in the blocks, as we were getting the highest resolution output from NERF itself. But here we are not getting the highest resolution. If the highest resolution here is considered to be 4n, we are getting an output, the feature space, if the dimensionality of feature space, if the number of channels in the feature space is nf, then for the corresponding to this n cross n image plane that we have considered for NERF, we'll get an output of nf cross n cross n, and then finally we pass it through the StyleGAN2 blocks, which gives us the output of nf dash cross 4n cross 4n, and then then we pass this through another convolution block that gives us the output of the shape of 3 cross 4n cross 4n, 3 corresponding to the 3 color channels. So yeah, earlier we have introduced this upsampling block in this layer, which we did not have earlier in the previous version of the architecture that we had considered earlier. So now this formulation looks better. We have done two things. We have moved volume rendering at a lower resolution, and we are no longer doing volume rendering in the image space. We are doing it in intermediate feature space, and instead of doing complete volume rendering, we are doing only approximate volume rendering. So yeah, with these two changes are very significant. They considerably speed up the forward pass to the extent that now it is possible to train an architecture that is combining NERF and StyleGAN2. But the suggested solutions still have some flaws. Hence, the authors proposed several changes to improve the performance. So the first is that they saw that the standard upsampling methods do not give good results. So upsampling methods such as pixel shuffle or LIIF, which is local image implicit function. This LIFF and or even something like pixel shuffle, it produces chessboard or texture sticking artifacts due to its tendency of relying on the image coordinates implicitly. In the second row, the second row results are, or the results shown for the upsampling method used in StyleGAN2, which is these bilinear interpolation. So the authors of StyleGAN2, they propose to use non-learnable upsamplers that interpolate the feature map with predefined low-pass filter. And while these upsamplers can produce smoother output, the authors observed non-removable bubble artifacts in both the feature maps and the output images as well. So yeah, we can see some bubble artifacts forming in the forehead of the feature maps, and yeah, in the forehead of the generated images as well. The authors, they find that their proposed upsampling method gives the best results, especially in feature space. We can see that their method looks the best. What they essentially do is the authors combine the two approaches, the approach used in LIFF and bilinear interpolation, to achieve a balance between consistency and image quality. So combining two approaches is essentially the theme of this paper. The architecture combines StyleGAN2 and NERF, and this upsampling method combines the one used in LIFF, LIIF, and bilinear. I'm sorry, I may have said LIFF. It's LIIF. And yeah, and the interpolation used in StyleGAN2. So with this, the final formula of their upsampling method is stated here. I am not going into the detail of how exactly pixel shuffle works or the details of this upsampling method. I encourage you to check out the StyleNerf paper and the pixel shuffle paper to go into the more details of how this upsampling method works. Then the second modification that they did was they fixed this 2D noise injection. So noise injection in StyleGAN helps the model to capture stochastic variation in the image. As you can see in this result, the no noise is shown in the right and with noise is shown in the left, and the with noise result looks much more realistic, while the no noise one, it looks a bit like an oil painting. But so yeah, the more stochastic variation, such as the texture of the skin, has not been captured in the right half. So So that part has been so that was the utility of noise injection in StyleGAN. The authors argue that this kind of noise, it only exists in the 2D plane, and since they are modeling the 3D representation of the face, it is unneeded in their model. But since something like this noise injection is necessary to produce stochastic variation, they need noise injection, but they don't need a noise injection the way it has been done in StyleGAN 2. So the authors propose a novel method to inject noise in the architecture. They propose this geometry aware noise injection method. So essentially what they do is, and by this method is only applied in inference, because this method requires correct density values to work. So it is only applied during inference. So what happens here is that once the authors have a 3D density map, they apply marching cubes on the predicted 3D density map to get the facial surface mesh, and they assign an independent Gaussian at each vertex of the extracted mesh and render the noise map via rasterization from the same view. So yeah, and so that's how they have, in a geometry aware manner, they have constructed a 3D noise map, and they perform rasterization to get a 2D noise map, and this noise map is then injected to every feature layer at n square resolution, which is the output of the nerve block before the nonlinear activation. So, and also to improve the results, we know that they are performing approximate volume rendering and not exact volume rendering, but for a set of randomly sampled pixels, they regularize the approximated volume rendering output to be close to the exact volume rendering output. So this helps to estimate the correct underlying geometry, or to improve the estimate of the geometry that they are modeling. And another thing which they do is they remove the view direction condition. So since they are dealing with single view images, as we know that NERV deals with multi-view images, so for NERV it is essential to condition the neural network on camera viewing direction, but here they are only dealing with single view images. So the view direction is not fed as input to StyleNerve. Instead, camera control is established by sampling the 3D points as per the desired camera view. So this is the loss function. The loss function, it's essentially a standard GAN loss, the non-saturating GAN loss, and we add this nerve path regularization that we discussed earlier, where we regularize the approximate volume rendering to be as close to the exact volume rendering as possible. And yeah, beta is a hyperparameter which is tuned, and the progressive training for the first T1 images, StyleNerve is, and they also have this different schemes based on the resolution. As we are dealing with a very complex architecture, they found that just standard training does not give the best results. So this is what the authors did. For the first T1 images, the StyleNerve is trained without approximation at low resolution. So this essentially the nerve path loss regularization will be 0 then, because we are not doing approximate volume rendering, we do exact volume rendering. And yeah, from T1 to T2, after T1 we start approximate volume rendering, and both the generators and discriminators increase resolution linearly. And after that the model is trained at the highest resolution. So at low resolution we train without approximation, but after that we train with approximation. We increase the resolution linearly, and then the model is trained at the highest resolution after T2 images. The implementation of StyleNerve is based on the PyTorch implementation of StyleGAN 2 ADA. The network is trained on 25,000K images with a batch size of 64, and the training takes 3 days to complete on 8 Tesla V100 GPUs. So the dataset, they validate their method on these 4 datasets. So FFHQ is human faces, AFHQ is animals, Met faces consists of these artworks. Since the number of images in Met faces is quite low, only 1336, they fine-tune the style nerf print on FFHQ for Met faces dataset. And the last dataset is the com cars, which is the dataset comprising of car images. So let's have a look at some of the results. So this is the qualitative comparison, or this image shows uncurated generation from style nerf. So this shows results of 512 cross 512 images, and you can see that the images look very good. The images are very high resolution images and of very high quality as well. On the top are human images, then we have these mid faces images and the animal images, and the images look very realistic for all the 3 types of dataset. This is again qualitative comparison of style nerf with other 3D aware models, so hologan, graph, pygan and giraffe, and you can see the comparison on AFHQ, FFHQ and comcards dataset, and if we see that the hologan images look they don't look good for all the datasets, and graph images also don't look good for all the datasets. There are significant artifacts. Then pygan, the human faces look decent, although the background does not look good at all. And yeah, the animal and cars, the cars is just, you can barely even make out that there are cars in those images. And the animals also, the animal faces look good, but there are significant artifacts around the boundary of the faces, the boundary of the animal face. And giraffe, the human faces look good, the car looks good, but yeah, the lighting seems off, and same goes for the AFHQ dataset as well. It also looks, the dog face looks good, but the lighting is off. On the other hand, without any doubts, the style nerf looks considerably better than the other models for all the 3 datasets, whether it's the cat images, the person images or the car images. So this is quantitative comparison of the results. So the lower these metrics, the better is considered the result. So all these methods, hologan, graph, pygan and giraffe, the FIDs of all these methods is very high in comparison to 2D GAN based methods. On the other hand, style nerf is considerably lower than these methods, as can be seen from the visual results as well, and it is very close to the 2D GAN, the style GAN based work, so that is good. And what style GAN based work cannot do is provide explicit camera control, which style nerf can do. And in terms of rendering time as well, you can see that that style nerf is considerably faster than pygan, graph and hologan. So yeah, because of the approximations and the changes they did in the architecture, they are able to speed up forward pass considerably. So this is qualitative result of controllable image generation, where they can explicitly control the camera pose. They are able to generate the face of this person from different viewpoints, and all the viewpoints look realistic. And I think this last result is particularly impressive. While you can say the body of the person is not perfect, but it still looks quite good. The neck and the shoulder, the way it's been captured, still looks decent. and it is consistent with, say, this frame, so this result is still very good. So this is the result of style mixing, as their method is based on the injection of style vector at different points in the architecture. It is very much capable of mixing the styles. You can see source A, source B, the skin color of this person has been transferred to most of the facial features of this person, and similarly likewise in other examples. So this is style interpolation and inversion results. So this is interpolating style. You have this image and this image, and they are interpolating style between the two. Here they are interpolating the style between two types of dogs, and here two kinds of this artwork. And yeah, they are also doing this with moving camera to show that their style interpolation is consistent with the camera control their model provides. They also show inversion with their method, and the inversion result looks good. And having obtained the inverted image, they can then rotate the camera and generate images of this person from different camera views, and then they can also combine their method with clip to further edit attributes of this person in the image. So some of the ablation studies are shown here. If they don't perform the progressive training we saw for first T1 images, they are training for low resolution. They are not doing the volume rendering, the approximate volume rendering. They are doing exact volume rendering at a low resolution. So if they don't do that progressive training scheme, if they don't employ that, they get artifacts of this sort where certain features look slightly off, they are not captured properly. And if they don't employ nerf regularization, if they don't regularize the approximate volume rendering output, then there are some of the other artifacts, as can be seen here. There are some artifacts around the facial boundary and background. And yeah, training with view direction also leads to certain artifacts, as can be seen here. The hair is slightly, yeah, it shows a weird pattern around this hair on the forehead, and this pattern is consistently, this pattern is sort of inconsistent across different views. So removing this helps the result. Removing the dependence on view direction improves the quality of the results. So some of the limitations of style nerf is that it does not really guarantee strict 3D consistency. While if we have implicitly assumed that we are modeling the 3D representation of the face, there is no strict regularization. The formulation does not guarantee that we are actually modeling accurate 3D geometry. And in fact, in the results we see that the style nerf is only able to recover coarse facial geometry. We are not able to recover some of the finer details of the facial geometry. So those finer details are all captured. Much of the heavy lifting is still being done by the StyleGAN2 synthesis blocks. So we are not able to get a good approach, because we are modeling geometry at a lower resolution as well. We are only able to recover coarse facial geometry. So that is a limitation, because it is very essential for the model to obtain fine facial geometry, because if we are able to obtain a fine facial geometry, then accordingly the results obtained of the person from different viewpoints, they will look good. If the facial geometry is not that good, then changing the viewpoints, the quality of generated images will also suffer. So this brings us to the end of this explanation. Thank you so much for watching.